So we're defining the complement of a quantum permutation to be the set of matrices M, such that M tensor ID and J commute for some D. Actually, I'll even go a step further. So there might be a matrix M and M tensor ID commutes for P, and then well, actually, if it commutes for P, it's got to be ID. So that's not what I'm thinking about there. So that's the commutant. It's necessarily an algebra. And the surprising thing is that it's a coherent algebra that is Sure-closed. Okay. And it's kind of interesting because the commutant of a set of permutations is Sure-closed in a classical case, but now we're finding that the commutant of a set of quantum permutations is Sure-closed, which I find quite intriguing. Okay. The other comment is that this commutant contains the coherent algebra generated by A. Now, the coherent algebra generated by A is the smallest coherent algebra that contains A. Now, A is an n by n matrix that's sitting in the algebra of n by n matrices. And the algebra of n by n matrices is a coherent algebra, okay, of dimension n squared. Okay. Now, A sits inside it. So we take the intersection of all coherent algebras that contains A. That is a coherent algebra that contains A, and it will contain J. Okay. So I won't say anything more about the moment, but it does contain that. Now, yeah. And so if we have a set, not necessarily even finite, of n by n quantum permutations, the commutant of the set is the intersection of the commutants of its elements. Okay. And that is again a coherent algebra. Okay. And as I was just saying, any coherent algebra of n by n matrices has dimension at most n squared. And it's a bit easy, if I start taking subalgebras and things, it's a bit easy to lose track of the dimension. So I'm remarking here, so I have coherent algebras C, D1, D2, and C is the intersection of D1 and D2, then the dimension of C is less than the dimensions of D1 and D2. The easiest way to see this is to remember that coherent algebras are subspaces. And so if you've got two subspaces in a vector space and the dimension of their intersection is less than the dimension of either of the factors or either of the terms. Okay, so this is just kind of a sanity check. And so, okay, so it tells us as we start, so if we might have a collection of quantum permutations and we pick the first one and we find the coherent algebra, and then we pick the second one and find its coherent algebra and form the intersection. And what's happening is the dimension's going down at each step, or stays the same. Okay. And I'll have another comment about that in a second. So in any case, if X is a graph and Q is its quantum automorphism group, which for the moment I'm just defining as the set of quantum permutations that commute with the adjacency matrix X, then that is a coherent algebra. Okay. It's a subalgebra, the coherent algebra generated by A. And just as a remark here, the smallest coherent algebra is just a span of I and J. And every coherent algebra contains that. Every system contains the identity for multiplication and contains the identity for show multiplication. So this is always in there. So this is just to give a picture. Any questions at this point? Okay, so now when it can, if X and Y are quantum isomorphic via a quantum notation P, then that's a definition of quantum isomorphic. Okay. So it's the same as definition of quantum automorphism, except now I've got a Y instead of an X. Now, despite we've got these matrices rejections, all the rest of it, this is, we can always drop back and just think of this as an ND by ND matrix, and this is an ND by ND matrix. And the comment I want to make here is that this matrix is unitary. Now, that's going to be an exercise. I should say something about that in a second. And so we've got P. Now, I can bring the P inverse over here, and so I get that these two matrices are similar. Okay, via the unitary matrix P. Now, in that particular case, I'm thinking of P as an ND by ND matrix, whereas my preference, usually I'm thinking of it as an N by N matrix with entries from some funny ring. Now, this implies that X, Y are co-spectral, but AX and AY are similar. But it's not, yeah, okay, so we'll leave it at that. This is, having this ID in there is a little delicate. So that certainly implies that X and Y are co-spectral because they'll have the same characteristic polynomial. Okay. So this is really going over something I said before. We have two n-bane matrices M and N, then Mn tensor ID can be written factored in this form, and M circle N can be factored in this form. And I either went through this very early in the course or it's in there as one of the exercises. So this is just standard fact. So the tensor product works nicely with the show product as well as the matrix product. And so, for example, if you look at P times AX squared tensor ID, then I can write like this. And so you get that if this holds for AX, it also holds for the squares and more generally for any polynomial. And so that if the CX is the coherent algebra generated by adjacent matrix of algebra graph X, and XY are quantumized something by a P, then the two coherent algebras are similar. Now we've got to be a little careful because these coherent algebras, this is really the coherent algebra. Well, I defined it the coherent algebra generated by AX. This should really be C of X tensor ID. Okay, but leave it as it stands. So that this statement is true, and since we can say these two things are isomorphic. So this implies that X and Y are co-spectral. Since these algebras contain the all-ones matrix and P commutes with the all-ones matrix, it also implies that J minus A of X and J minus A of Y are co-spectral. So the graphs are co-spectral with co-spectral complements. So this is stronger than just being co-spectral. Okay, it's a somewhat surprising fact that co-spectral graphs tend to have co-spectral complements a lot of the time. Okay, it's not a requirement, it's just the way things work out. The problem here, as I said, well, I've got this comment, this is not a type of isomorphism as listed before. I talked about the three different versions of isomorphism of coherent algebras. And this is slightly different because in principle, we have this tensor ID floating around. Okay, and I won't say it's not known what difference that makes, but it's not known to me what difference that makes. Okay, and so I'm just supposed to treat it cautiously if I need to, but for what we're doing now, it's not so important. So we can always sort of push our way down and say that these two matrices have the same characteristic polynomial and they're symmetric and therefore they're similar and things like this. But having that tensor I in there can make isomorphisms a little more delicate. And so finally, I'm going to use C sub Q of X to denote the commutant of the quantum morphism group of X. And this is a coherent algebra which contains the coherent algebra generated by X. Okay, so we have these coherent algebras. Yeah, okay, so that's all I want to say about coherent algebras for now, which might be a relief. I want to talk about constructions, lean towards talking about some of the constructions of graphs that are quantum isomorphic, but not classical isomorphic. The list is actually fairly short, but it takes some time to do it, cover some of the details. So I need to talk about group rings. These will also serve as examples of coherent algebras. Okay, so more of that. So I'm going to start with the finite group. My groups will be finite. A quantum group, when people talk about quantum groups, is generally not finite. But so that to be a finite group, the group ring over the ring R is often defined as a set of formal sums of the form sigma A sub G, A and R, A G and R times a group element. Now, this is a bit like the formal and informal power series. I do not know what that word means in those sentences. It doesn't have a mathematical meaning, as far as I can tell. If anybody's got it. But this would be the standard jargon. And so then you add these and multiply them in much more or less the obvious ways. Now, I like to be a bit more precise on definitions on occasion. So the point about this sum, first thing, it's only finite in many terms in this sum and not zero. Now, if you write down an infinite sum, then somewhere in the background there's hiding some topology because the sum has to be defined in terms of convergence because of the actions of set theory, we can only compute a finite number of sums. We don't have time to do an infinite summation. Okay, so we only deal with finite sums. So that's the first thing. Secondly, this is effectively just a sequence. It's a sequence of elements of R indexed by group elements. Okay, so I didn't write it down. Yes, I did. No, I didn't write it down. Okay, let me do it. So you're actually dealing with functions from the group to the ring. Okay, so you've got the group L and G in this particular term. Yeah, okay, functions from G to the ring with finite support. Okay, you're not allowed to. Okay, so you have to distinguish between the two cases. Anyway, so you could think of them either as, well, once you get a little bit of practice, there's no particular reason not to think of them as formal sums, but just be warning you that the term formal sum doesn't have a meaning, but you can give it one if you care enough. Now, the summation is obvious. I've written out the multiplication here, so you're just multiplying things. You expand them, and so if you've got m terms here and n terms here, there are mn terms in the product, each of which is a scalar times the product of group elements, and so then you group the group elements that are equal, and so you get a formula like this. Now, this formula is often called convolution. But so you can multiply them. And so life's going to be a bit easier for us in a second because we won't be doing it in this degree of abstraction. Yeah, so as I said, to be rigorous, the elements of the group ring are functions from G to R with finite support. And the convolution often might be denoted by F star G, which is a bit risky in our setting because we're using convolution if we've got at least one other convolution in play. Okay, but so that's repeating more or less what I said. And now what we'll actually do is we won't be thinking of these things as sequences of finite support. We're going to assume that our group has got order n. And so then we can represent the elements of the group by n permutation matrices. Okay, and so then we have a map from the group into the the n by n matrices over the reals. And this map is an isomorphism. Okay. And so in that point, we can now, and so certainly if I have a map from G into the matrices, I can extend that to a map from the group ring into the matrices, because the elements of the group ring are just sums of these matrices. Okay, and so that means if provided we're willing to identify the group with these n by n permutation matrices, we can view the group algebra as just a subalgebra of the n by n matrices over reals. Now, it could be over the complex numbers. It's more likely to be complex numbers, but it's not going to affect anything we do right now. Okay. Now, okay, so we're going to take the view that the group ring, what it's worth, is a subalgebra of the algebra of n by n matrices over the reals of the complexes. Now, this subalgebra is a coherent algebra. The permutation matrices are 0, 1 matrices that sum to the all ones matrix. Okay, and so they form the canonical basis. So this is just now the group theorists would never call this, say this is a coherent algebra, but it is. And you've got the regular product and you've got the Schur product. Relative to the Schur product, the permutations themselves or distinct permutations have Schur product 0. Okay, but it's there we are. Again, any questions at this point? Now, if you're trying to work out information about the group for the matrices, it turns out it's important to consider the center of the ring. So these are the elements, or the center of a ring is the set of elements of the ring that commute with everything else. Okay, so the identity element lies in the center, so the center is always non-zero. And now we're concerned with the center of the group ring. Basically, because you're trying to study questions about homomorphic images of the group ring, and it turns out that it's very useful to consider what happens to the center at the same time. So we're viewing subsets of G as sums of permutation matrices. If I say S is a subset of G, then you can assume that I really mean the sum of the permutation matrices correspond to the elements of S. Okay, so representing sums and subsets are the same thing. Now I'm interested in what things in the center. Now, if S is a subset of G and X is in G, so we're assuming that. Now we want to know what does X commute with S. Well, let's assume it does. And yeah, so we're going to X commute S, and I'm choosing an element A of S. Now, if A is in that case, if A is in S, then XA is in SX, and that means that XA is equal to BX for some B in S. Okay, so if this is true, and A is an element of S, then XA is equal to BX. Okay, and so now I can bring the X over here, and I get B is equal to XA in X inverse. So the jargon is that this is a conjugate, that B is a conjugate of A. If you're thinking about your linear algebra, these would be similar. If A and B were matrices, in fact they are, these matrices would be similar. Okay, I usually put X inverse AX, but for once I do it this way. So the conclusion is that if X commutes with S and A is in X, then this conjugate is also in S. Okay, and so then the conjugate, so that means that XB, X inverse, is also in X. So I can keep on taking conjugates. And so for each element that commutes with S, I get a bunch of conjugates. Okay, and so the conclusion then is that if, so what we have is, this is true, that if A is in S, then XA, X inverse is in S. And so the conclusion is that X inverse is equal to S. So for each element, little s, a big S, X, little s, X inverse is equal to something in S. So now, did I do it? Well, I can now multiply on the left, right by X, and I get XS equals SX. And so S commutes with X. So the moral here is that if S is a union of constantly classes, well, then it commutes with every group element, and conversely, if the commutes with every group element is a union of distinct constantly classes. Conjugate class of A is a set of all elements that are conjugate to A. Now, being conjugate is an equivalence relation, so you get a partition into equivalence classes. The equivalence classes are called conjugate classes. And what we're saying is that the set S is in the center if and only if it's a union of conjugate classes. Okay, and so now we know show you an explicit description of the center. Well, we may have spent quite a while searching for the sets S for a moment, but let's leave that. And so we also know that the number of conjugate classes is going to be the dimension of the center. Everything in the center is going to be a linear combination of things which are buried under conjugacy. So everything is a union of conjugate classes. So the conjugate classes will be a basis for the center. Okay. Now, okay. So now the consequence of this is not only is the group ring itself a coherent algebra, but the center is a coherent algebra. It effectively establishes closed under multiplication. And if two sets S and T are disjoint, then the corresponding sums have shared product of 0. So we have a second coherent algebra. Okay, now this coherent algebra is commutative, and it's also homogeneous. It certainly contains, well, the conjugate class of the identity is just the identity by itself. Okay, and so actually it's possibly a little bit first called next size, but it's easy enough to see then that it's actually homogeneous. So we have the coherent algebra formed by the group algebra, and sitting inside that we have this homogeneous commutative coherent algebra. And in fact, in courses in representation theory, they don't use this jargon, but you spend your time working with this particular algebra, the algebra generated by the center. That's the one that matters. You can always, in some sense, you can always reduce the questions about the center, but we're not doing group representation theory, so we'll leave that for now. I'm not going for time. I finish early today. So since it's commutative, it's an example of what I've alluded to a few times as an association scheme, but that's not going to play a role. So I want to look at a particular example. This is probably, so I want to look at the symmetric group on 4 letters. Okay, so it's got 24 elements. Now, each element is a permutation, and you can write them out in cyclic form. And so if you look at this list here, you'll see I've got all possible, in fact, I've got all possible forms. You have the identity permutation, Okay, that's clearly a conjugate class by itself. And so now you can think, well, the things, the transpositions, they're all conjugate, and therefore choose 6 transpositions. There's the double transpositions, of which there are exactly 3. Okay, that's these guys. There's the 4 cycles, of which there are 6. You fix the first element as 1, and you've got 6 ways of rearranging 2, 3, and 4. And then you've got elements which fix 1 point and act like a 3 cycle on the rest. So you get 4 choices for the first point, and then you have either 1, 2, 3 or 1, 3, 2. So you get 8 elements in this conjugate class. Okay, so as these elements, the conjugate classes of these elements are the complete list of conjugate classes for this group at Sim4. Any questions? Now, so for each conjugate class corresponds to a matrix, and a matrix in the center. Okay, and so for the identity, we just get the identity matrix. Now, if the conjugate class has got size 3, then each row of the matrix is going to have 3 non-zero entries. Okay, and so you get a matrix, a 24 by 24 matrix, giving you a cubic. Actually, it would be a cubic graph. So it's this permutation is equal to its inverse. You'll get a cubic graph on 24 vertices with valency 3. If you use the transpositions, you get a 6 regular graph on 24 vertices, 6 regular, 8 regular. Now, I'm not saying that each of these is connected, but it's not a problem. Now, so what I've listed here are the eigenvalues of these matrices. Okay. Now, the point here is that since my matrices in the center commute, then you can, and since everything's closed under transpose, you see they're commuting normal matrices, and so you can simultaneously diagonalize them. So in other words, there's going to be a collection of eigenspaces or collection of subspaces on each of which, so you pick a subspace, I'll say pick this one, and then each matrix on that subspace will act like a scalar matrix. So that subspace will consist of eigenvectors for each of the matrices. Now, the eigenspaces for the matrices can be a little bigger, but we're looking at eigenspaces for the entire set. And so what this is telling us here is that there's one-dimensional eigenspace, which is just spanned by the constant vectors. Okay, there's a second one-dimensional eigenspace, which is arising from the sign character of the symmetric group. I won't go into details. That's a one-dimensional representation. There's a two-dimensional representation. Now, S4 has a homomorphism onto S3 because there's a Z2 cross Z2 sitting normal. Okay, and the symmetric group on 3 letters has a two-dimensional representation. So that's what this is. And then you get 2 representations of degree 3. So that's telling me that these, you can just view these as the multiplicities of the eigenvalues. Okay, so we say this graph has got an eigenvalue 6 multiplicity 1, minus 6 multiplicity 1, 0 multiplicity 2, 2 and minus 2 each multiplicity 3. Okay, now since the least eigenvalue of this graph is equal to minus the largest eigenvalue, this graph will be bipartite. Okay, that's not too hard to see, and so will this graph be bipartite. Okay, this guy is probably not even connected, but I'm not going to go into that. Now, how do you get this? Well, the fastest way is to type in character table of Sim4 into Google, and it will produce it. There isn't really a sort of a canonical algorithm for doing this. I mean, it is possible to do it. It doesn't require any great feature intellectual effort. It's not the most fun programming you would ever done if you have to do it. So generally look it up rather than do it yourself. The problem is if I give you a matrix, you can diagonalize it. There's code for doing that, no trouble. But now you've got 2 matrices and you want to find the common eigenvectors. And that's not, well, that's not theoretically difficult. It's just annoying when you're trying to write the program. And if you've got more than 2 matrices, then it gets worse. Okay, so I'm just being lazy and taking this as given. Okay. Now, in fact, there are formulas, well, there are algorithms for computing the entries of this table for the symmetric groups. Okay, so I could also appeal to that. But the point simply is that I now have this symmetric group. We have these quantity classes, and we've got their valencies and eigenvalues. Now, the second thing is each of these, the graphs we get here will be a Cayley graph and the connection set will be the quantity class. Okay, so staring at us there, we have, well, that's not right. Well, we've got 5 Cayley graphs. That's not the first one's not the most interesting. So we have 4 Cayley graphs. Okay, and so, and then of course, if I take the connection set, the union of C1 and C2, then I've still got a graph, and I know what the eigenvalues are. There'll be 3 plus 6, 9, 3 minus 6 minus 3, 3, 1, and minus 3. So I can work out the eigenvalues for any Cayley graph whose connection set is a union of constant classes. Now, you know, if I was teaching a course in association schemes, you would know how to compute this before the end of the course. So it's not something that's beyond us in any sense. It's just that I choose not to spend the time there. So for this particular case, we know the know what's happening. And there's already something a little funny happening here, because if you look at the eigenvalues for C2 and then look at the eigenvalues for C3, those two graphs are going to be cospectral. 6, eigenvalue minus 6, eigenvalue 0. This is 2 and minus 2, but it's got multiplicity 3, and this is minus 2, multiplicity 3. So those two things are cospectral. Okay. Now, as it happens, they're not isomorphic. Okay. And so there's various ways of proving that. The most reliable way is to stuff the graphs into something like Sage and compute and test if they're isomorphic. You can also often, in these situations, if you look at the neighborhood of the vertex, so each of these graphs has got valency 6, and so you get a 6 vertex graph as the neighborhood. And I haven't actually checked, but if the neighborhoods aren't isomorphic, the graphs aren't isomorphic. Or sometimes you can look at you can look at cliques of a given size or co-cliques of a given size. But generally speaking, if you want to prove two graphs are isomorphic, the fastest way is just to stuff it in order. You know, are these isomorphic? And that works for graphs on thousands of vertices. And graph isomorph routines are faster than the routines for solving sets of linear equations. So, I mean, you know, it's not a particular problem generally not a problem in practice. Okay, so we have this information about the symmetric group in 4 letters. We have 4 non-trivial Cayley graphs, okay, and plus certain, we can take C1 plus 3V plus C4, so we get a bunch of graphs there. For each of these graphs, we know the spectrum. Okay, now the actual jargon here, this is a form of the character table of the symmetric group for 4 letters. The actual character table will be scaled a little differently, but this is the version we need because it gives me the multiplicities and the eigenvalues, and I identify the quantity classes. Any questions? So I actually want to pick out 2 graphs. If I take C1 union C2, then the connection set consists of all the elements of the symmetric group of order 2. Okay, they're the involutions. If I take C1 and C3, I'm taking all the elements of the symmetric group with no fixed points. This has got 4 fixed. This has got 4 fixed points. This has got 2. This has got 1. These 2 have 0. So they're the derangements. So we get 2 graphs. The graph on involutions, the graph on derangements. They're both 9 regular graphs on 24 vertices. And to cut to the chase, they're quantum isomorphic. We'll get there. I'll improve it. Now, again, what are the eigenvalues? Well, they're 9, minus 3, 3, 1, minus 3, oops, but then it's minus 3, 1, same multiplicities. So they're cospectral. Now, I said I want to get quantum isomorphic things, and if I have 2 graphs that are quantum isomorphic, then their coherent algebras are isomorphic, and that means that the matrices I'm looking at, the graphs or adjacency matrices, must be cospectral, and the complements must be cospectral. But these are regular graphs, so if regular graphs are cospectral and the complements are cospectral, so that's why I care about the spectrum. So I have 2 graphs, and The okay, I suspect they have the same coherent algebra, but I haven't tried to check. It's presumably just the coherent algebra, just the center, but I haven't tried to work it out. So, so the claim is, and I'm not going to, is that these two graphs are quantum isomorphic, and these are the smallest known pair of quantum isomorphic graphs. So I've told you how to construct them. They're Cayley graphs for these connection sets. So you don't need that table I was showing you. Just say, well, I've got the elements of order 2. There are the 6 transpositions and the 3 double transpositions. That gives me a Cayley graph, a 9 regular graph on 24 vertices. Or I can take the derangements, of which there are also 9, and I get a second Cayley graph on 24 vertices. And I said, well, given that table, these two guys go spectral. So I want to go on and give more examples. So what examples do we have for quantum isomorphic graphs? In a sense, the list is fairly short. There is one construction using games, which gives an infinite series. And Roberson took the smallest examples from there and fiddled with them and came up with these two, with the pair on 24 vertices. I'm not sure I'll consider these part of that infinite series. So there is that infinite series defined in terms of certain class of quantum games. The description is fairly complicated, and I'm not about to try and go through it. Okay, we do get these 2 Cayley and 24 vertices. Simon Schmidt produced examples rated to something called the E8 root graph on 120 vertices. This is a strongly regular graph, and there's a family of other graphs, each of which is quantum isomorphic to this. And the Hadamard graphs, which I'm going to go through in a bit of detail in a moment. Now, the point I'm making, well, there are infinitely many Hadamard graphs, but in a certain sense, we don't have much in the way of examples. Okay. In terms of graph and actual concrete examples, that we try and write down, we have these guys and these guys. Maria has also found a few related, some extensions of this, but the list is fairly small. The secondary mark is in the first 2 cases, the graphs we're getting, which are quantum isomorphic, are also related by what I was calling local switching. So that's an operation we have which preserves isomorphism. And so, and it's likely true, but it's quite possibly true that in the general case for the games that they're coming from local switching too, but I haven't had a chance to go into that. The Hadamard graphs, well, I'll say, I'm going to go through those in a minute. So they're related by local switching, and it turns out that the quantum isomorphisms are block diagonal. So there is some structure there. But I mean, almost any question you ask me beyond that, I'm going to say, I don't know the answer, and I don't think anybody else does either. Okay. I mean, this is all pretty much bleeding edge. So we have these information. I mean, Schmidt's result was just last year, I think. The Hadamard graphs was probably about a year ago. Okay, so I want to talk about these because they are a big combinatorial class. So I've defined Hadamard graphs a number of times, or Hadamard matrices a number of times. But now I want to talk about Hadamard graphs, which are graphs we get from Hadamard matrices. So a Hadamard matrix is an n by n matrix with entries plus or minus 1, such that h transpose equals n times I. So 1 on root n times h is orthogonal. And in that case, the entries are all the form plus or minus 1 root n. So that's a Hadamard matrix. And they're important operations. They're important in coding theory, they're important in design theory. They come up in some questions analysis. They come up all over the place. So, and they've been an object of interest in combinatorics for many, many years. Now, I'm just going to give you 2 concrete examples. This is a 2 by 2 Hadamard matrix. And so this matrix here, it's scrappy. So -1 diagonal, 1's in the off diagonal. This is a Hadamard matrix. Okay. So there they exist. The Kronecker product of two Hadamard matrices is a Hadamard matrix. So once I have one, I get infinitely many. Now, if a n by n Hadamard matrix exists, then either n is equal to 2 or n is divisible by 4. Now, that's not too hard to prove. If you've got a Hadamard matrix, you can always, one operation which takes Hadamard matrices is to multiply rows or columns by -1. So if you give me a Hadamard matrix, I can always scale multiply columns by 1 and -1 and arrange for the first row to be all ones. Let me actually do some of this. So I can assume that if there's a Hadamard matrix of order n, then there's a Hadamard matrix of order n where the first row consists of ones. Now let's think about the second row. It's a 1 - 1 vector, which is orthogonal to the first row. And so that implies that n is even. So I've established that the order of Hadamard matrix must be even. Now, so in fact, what's going to happen then is we're going to have the second row is going to have some ones and then minus. So if this is 2m, the first row is just m1s. The second row we can assume to be 2m1s for the first row, m1s and m -1s. So now we go for a third row. And when you try and work that out, then you'll get the condition that 4 divides n. Okay, so I'll leave it at that. So it's now the converse. If I have an integer n divisible by 4, is there a Hadamard matrix? That's been an open question, probably since Hadamard first wrote down Hadamard matrices. And the smallest open case, I think, is still less than 1,000. Now we have zillions of constructions of Hadamard matrices of all orders, but the problem is, given a prime p, is there a Hadamard matrix of order 4p? And the first prime fails. It is, I think, probably less than 200. Okay. Now, and as I said before, if you've got two Hadamard matrices, the Kronecker product is a Hadamard matrix. Now, the next result I'm proving, well, I'm essentially just doing it because it's an example of the sort of things you can do with Hadamard matrices. It won't really play a role in what follows. So a Hadamard matrix is regular if each row and column sums are all equal. Now, what I'm going to prove here is if you have an n by n Hadamard matrix and the row sums are all equal to alpha, then n is equal to the square of alpha, and the column sums are also all equal to alpha, but I didn't bother to write that down. But the important thing is that if the Hadamard matrix is regular, then n is a square. So this is a restriction. Okay, and so what happens is you start putting restrictions on Hadamard matrices and ask them to be a bit more special. You'll often find that the condition now is that n has to be a square. Anyway, so here's a proof. So we're assuming that H applied to the all ones vector is alpha times the all ones vector. So each row sums to alpha. And all I'm going to do is multiply on the left by 1 transpose, and 1 transpose 1 is n. So we get this. Okay, now we haven't used the fact that we've got a Hadamard matrix yet, but if this is true, why isn't this working? If H is equal to this, then I can multiply both sides by H transpose until I get alpha H transpose 1 is equal to H transpose H times 1. Well, that's n times I, so it's n times 1. And so now I multiply this on the left by 1 transpose, this, I get this. And so you get that, I'll bring the alpha over here, so you get that alpha inverse n squared is equal to 1 transpose H transpose 1, which is equal to this, just take transposes, which is equal to this. And so then you get that alpha squared is equal to n. Okay, so this is the calculations are sometimes necessary in Hadamard matrices. It's just that, and I'm saying if you impose restrictions, you get extra properties. Okay, but what are we going to do with Hadamard matrices? We're going to construct Hadamard graphs. Now, actually, not an interesting question who this is due to. Do you have any ideas, Ada?
Actually, no.
What?
I don't know where it came from.
Yeah, I'm not sure. I mean, it's a natural enough idea. comes up in various contexts. Anyway, so let's go on. So the point about Hadamard graphs is they're going to be, well, we'll see that they're quantum isomorphic, but we'll get that a little while, we'll get that point. So we've got a Hadamard matrix. Now, so it's an n by n matrix. I'm going to construct a bipartite graph on 4 n vertices, and that would be my Hadamard graph. Okay, now for bipartite graph on 4 n vertices, I expect to see 0 matrix transpose 0. So that matrix has to be 2n by 2n by 2n. So the Hadamard matrix itself is not going to work. Okay, now the idea roughly is that you, in your Hadamard matrix, you've got 1s and -1s. But we're graph theorists, we want 1s and 0s. So we're going to replace each one by a 2 by 2 identity, and done it again, and each -1 by the matrix 0, 1, 1, 0. And that will give us a bigger matrix of order 2n by 2n, and that's what we'll use. Okay. Now, because I need to, or wanted to actually work out the eigenvalues for the graph I'm constructing, I need to be a bit more detailed. So if I have a Hadamard matrix, I can write it as the difference of 2, 0, 1 matrices, which I'm going to call H plus and H minus. So you have these two matrices, their share product of 0, and they sum to the all ones matrix. Now I'm defining n to be this sum. Okay, so as I'm saying here, I'm replacing the -1s in H by this, and I'm replacing the 1s by this. And we write that using Kronecker products. And so this is my matrix. And so the adjacency matrix out of my graph is this guy. So this is a recipe. You can get tables of Hadamard matrices off the internet, and then you can sit there and merrily construct graphs by this procedure. Okay, it's nothing too complicated. Okay, I'm not sure it's strictly necessary. So what about the eigenvalues? So my point about these graphs is the graphs we're constructing are highly regular, and in particular they have a small number of eigenvalues. I'll say a little about that in a moment. So the idea is that these two matrices commute, well, this is the identity for heaven's sake, and they're both symmetric, so they can be simultaneously diagonalized. And I'm going to do that. Now, when I diagonalize this, I just get the same matrix back again. And the eigenvalue is this matrix 1 and -1. So I'll get a diagonal matrix with 1 and -1 as a result. But let's just do this one step at a time. So the change of basis matrix I need is this. These are the eigenvectors of the, these are in fact the eigenvectors for the 0, 1, 1, 0. Then this is an orthogonal matrix, so L transpose L is equal to identity. And well, this is trivial L transpose identity. L is equal to the identity. And L transpose 0, 1, 1, 0 L is equal to this. Okay. And so consequently, you get, when I can apply this on the left to n and on the right, or the transpose on the left and the matrix on the left, and I get this. So in other words, n is similar to this matrix. Okay. Now you can basically recommute the rows and columns of this matrix to make a block diagonal. Okay. So there's a permutation matrix P. Basically, the permutation matrix P, which brings it into this form. So it's now block diagonal. And so I've got details there which we don't really need. This matrix is similar to n. Now this is just the all ones matrix. And this is just our original H. Well, written down here as well. Okay. And so n is similar to this. And well, the graph we're constructing is bipartite. And so the eigenvalues are symmetric about the origin. And so it's often easy to work out the eigenvalues of the square of the matrix first and then take square roots. And if you do that here, you discover that the square is similar. Oops, I don't really want to use blue there. Let me go back to my fancy colors. So the square is similar to this. Now J is the all ones matrix. J squared is n times J. So I know the eigenvalues of that. They're n squared and 0. And H transpose H is n times I. So from that, you conclude that the spectrum of A, is minus n multiplicity 1 minus n multiplicity 1 coming from here. 0 is multiplicity n minus 1 coming from here. And then two eigenvalues root n and minus root n, each multiplicity n. So I've worked out the spectrum of this bipartite graph. Now, this bipartite graph is a Hadamard graph. And one conclusion from this is that the Hadamard graph is distance regular. Now, I'm not going to explain that. You can look it up in various places. But that, that's, so they're very special graphs. They've got a lot of symmetry, they've got a lot of regularity, and they encode Hadamard matrices. And so this is working out perfectly. So Manchester and Robertson proved that two graphs are quantum isomorphic if and only if each planar graph is Z, the number of homomorphisms from Z to X equals number from Z to Y. Now, this is plain old-fashioned graph homomorphisms, I think quantum. Okay, so quantum isomorphic is implied by equality of homomorphism counts. Now, computing number of homomorphisms from Z to X is not something you would ever want to do. Okay. Yeah, eight is winning. It's so, but that is an explicit formula. The other point we'll be a little bit careful here. There are two notions of quantum isomorphism, and this is some sense the hardest one, but it does not going to matter. So they have that theorem, and so then, well, Ada is sitting there grinning at me, and Bill Martin, and independently Daniel Gramada proved Hadamard graphs of the same order are quantum isomorphic. Okay. And now the point is there are lots of Hadamard graphs. And so this gives you large families of graphs that are quantum isomorphic. And their proofs use the result of Manson, Screw, and Robertson. The problem, well, okay, so that's nice. We now have a lot of graphs that are quantum isomorphic, okay? We don't have an actual example of a pair of Hadamard graphs with a non-trivial quantum isomorphism one to the other. And that's an interesting question. We really would like to have that. But as I say, we know that they're all quantum isomorphic. And the proof goes through this homomorphism counting. We don't have a way of constructing an explicit isomorphism for even one pair of the mixed matrices. So nor do we know the quantum morphism group of any Hadamard graph. And I just want to finish off. There are some things. There are two trees are quantum isomorphic. They're isomorphic. There are a couple of proofs for this. I might talk about this another time, but I think that should be the end. And that's me doodling here. Okay, so I'll stop there.